So we have been looking at this question of reachability in a graph. So we said that to find whether a vertex is reachable for a target vertex is reachable from a source vertex, we systematically explore the graph. We mark the source vertex and then we go to its neighbors, mark its neighbors, and keep doing this systematically until the target becomes marked. So what we saw last time was that in order to do this as a procedure, we have to have a way of representing the graph which is not a picture. So we came up with these two different representations. The adjacency matrix has a row and a column for every vertex. So remember that we are assuming that our vertices are always numbered 0 to n minus 1 for convenience. So if we have an entry at row I, column j, it indicates whether or not there is an edge from I to j. So if it is a 1, it means there is an edge. If there is no 1, if it's a 0, it means there is no edge. And then we observed that this could be a wasteful representation if there are not that many edges. A number of entries in this matrix are 0. So instead we could just record an adjacency list for each vertex. So just record the neighbors. So if we go back to this graph that we had just now, so if we look at V4 for example, so V4 has an outgoing edge to V0, an outgoing edge to V3. It also has an incoming edge from V0 and V3. And then it has an outgoing edge and an incoming edge from V7. So the neighbors of 4 are 0, 3 and 7. So if you look at this adjacency matrix, it says that in the neighbors of 4, if you look at the row 4, it has 1s at positions 0, 3 and 7, right? And here, it doesn't have, so there is one entry missing here. So it should be 0, 3 and 7, right? So this is how we would represent the matrix as either, the graph as either an adjacency matrix or an adjacency list. So what we are going to look at now is the second part of the story, which is having represented the graph in this way where we can manipulate it, how do we actually systematically explore the graph? So we did a kind of ad hoc exploration last time using the adjacency matrix, but this time we want to do it systematically, and there are two systematic ways to do this. One is called breadth first and one is called depth first. So first we will look at breadth first. So when we explore a graph breadth first, we do it level by level. So we start with a vertex, then we identify all the neighbors of this vertex, that is all the edges which connect this vertex to its neighbors. We look at those endpoints and say that these are now all reachable from this vertex. Then we go to those neighbors and look at what is reachable from there. So these are things which are 2 levels away. So 1 level away are the neighbors of the source vertex, 2 levels away are the neighbors of the neighbors, and so on. Now what happens of course is that we might end up with a situation where we start with 5, right, and then we identify its neighbors as say 3, 8 and 7, and then we go to 3 and then we identify its neighbors as 4, 6 and 1, no, 4 and 6, sorry. And now I look at the neighbors of 6 and it says, oh, 5 is a neighbor of 6, but we started with 5, right? So we need to record that a vertex has been visited, and we need to make sure that we don't visit a vertex twice, otherwise we'll go round and round this kind of a triangle or a cycle a number of times, right? So we need to do this visiting and exploring. So exploring means we go from there to one more level of neighbors. So we need to do this visiting and exploring exactly one per vertex. So we need to maintain some information, right? So we need to maintain information about which vertices have been marked as visited, that is, which vertices have been marked as neighbors of something we have already seen. And in the process of exploration, these have been marked, but we still haven't looked at their neighbors. So there is a subsequent process after visiting a vertex of exploring its neighbors. So whether or not such a visited vertex remains to be explored. So we need to keep two things, right? Has it been visited? Has it been explored? So of course it will be explored only after it is visited, but if it has been visited and not explored, that means this is some pending work that we have to do. So as we said, we will always assume that if we have n vertices, we call them 0 to n minus 1. So here is an undirected graph with 10 vertices numbered 0 to 9. So what we will do is record the visited information as a function. If you are thinking about it in programming terms, in terms of the computational thinking course, you can think of it as a dictionary whose keys are 0 to 9. It doesn't really matter, but it's actually mathematically a function. For each vertex, it tells us true, the vertex has been visited, or false, the vertex has not been visited so far. So initially we assume that no vertex has been visited because we have not explored the graph at all. So initially visited of v is false for every vertex. And now we also separately have to look at the vertices which have been visited, that have been marked true by visited, but which have not been explored, right? So exploration means looking at the neighbors of that vertex. So we have not yet looked at the neighbors of that vertex. So we have to keep a record of this. So this is a sequence of vertices which have been so far visited but not yet explored. And we will keep this in a special kind of sequence called a queue. So queue has exactly the meaning that you associate with an English queue. So if you're standing in a line to buy a ticket, right, a queue forms, you join at the end of the line. The person at the front of the line buys a ticket and moves away. The next person moves up to the front of the line. And gradually as you move forward, when you reach the head of the queue, you get your turn. So the same way we will maintain these vertices in a queue. As they get visited, they will be added to the queue. When their turn comes, they will be explored. So exploring a vertex technically means the following. We want to look at all the edges which are outgoing from that vertex. So we look at every edge ij which is there in the graph. And if we have not yet visited j, then we mark j as being visited and we add j to this queue of unexplored vertices. So j has been marked now as visited. So it is due to be explored when its turn comes. So we put it at the end of the queue. So suppose we start our BFS from a vertex j, right? So what we will do is initially we will set visited of this vertex to be true because we start there. So we have visited that vertex and now we have to explore it, right? So what we do is we just put it into the queue because our procedure is going to be to systematically explore all the vertices which are in the queue. So we set the visited of j to true and we add j to this queue. And now what we do repeatedly is we keep removing the vertex at the head of the queue. So this queue, as I said, is a line of vertices waiting to be explored. So we pick up the next one which is waiting, which is at the head of the queue, the front of the queue, and explore it, right? And exploring it, as we said, is to check whether its neighbors which are visited, its neighbors have been visited or not. So if a neighbor has not been visited, we mark it as visited and put it in the queue. So how do we stop? Well, if there is nothing in the queue to visit anymore, to explore anymore, this means that we have visited vertices and all the vertices we have visited, we have explored and there is nothing left to do, right? So when the queue becomes empty, this breadth first search, as it's called, BFS, terminates. So let's try an exploration of this graph. So let's assume that we start at this vertex 7, right? So we are going to start with 7. So as we said, initially we have set visited to false for all the vertices and initially we have this queue. So the queue, I'm going to assume, has the left side as the front and the right side as the end. So the head and the tail of the queue. So we join from the current tail of the queue and we leave from the head of the queue. So initially the queue is empty because we haven't started anything yet and initially everything is unmarked. So everything is visited set to false. So we are starting from 7. So the first thing we do is that we mark 7 as visited, right? So we mark 7 as visited, right? And just to illustrate, we have also marked it on the graph, okay? And now we have also put 7 in the queue saying that 7 needs to be explored, right? So we mark 7 as visited and add it to the queue. Now the real breadth first search starts, which is you pick up the first element in the queue and explore it. So we pick up the 7, explore it. So what are the neighbors of 7? The neighbors of 7 are 4, 5 and 8, right? So in this process 4, 5 and 8 get marked, right? And now they also get added to the queue. So I put them in some order. I've just put them in this particular case in ascending order. It doesn't matter. I could have put it as 8, 5, 4, 5, 4, 8, but it's just convenient to put it in some fixed order. So I always put them from smallest to largest. So 4, 5 and 8 were neighbors of 7. They had not been visited. So now I have marked them as visited and added them to the queue. And notice that 7 has gone from the queue because 7 has been explored. So 7 is no longer in the queue. Now the first vertex in the queue to be explored is 4. So the next step is pick up the first vertex in the queue and explore it. So I explore 4, right? So if I look at 4, it has neighbors 0 and 3 and 7. But 7 has already been visited, so I don't have to do anything about 7. I pick up the 2 which have not been visited, which is 0 and 3, and set their visited status to true. And I add them in the queue in some order. In this particular case, as I said, I will put 0 before 3 just because it is a smaller number. So now I have finished with 4. So 4 has left the queue, but from the previous round 5 and 8 are still pending, right? So 7 added 4, 5 and 8. I finished 4, 5 and 8 are still pending. So 0 and 3 will have to wait their turn. They will have to wait until we have finished. So in some sense 4, 5 and 8 were one level away. So until I finish all the vertices which are one level away, I am not going to explore the vertices which I added at level 2, namely 0 and 3. So what I do is I now pick up 5 and explore it, right? And in the process I look at the neighbors of 5. So they are 3, 7 and 6. But 3 and 7 have already been visited so far. So we don't have to look at them again. But 6 is new. So I mark 6 and I put it in the queue. Similarly, now I'll pick up 8. And from 8 again I have vertices which are 5, 7 and 9. But since 5 and 7 were already visited, what is added now is 9 and 9 gets put into the queue. Right? So now I finally finished the level 1 vertices in the queue and I have come to the 0 which was added at level 2. So I explore the 0. So 0 has 3 neighbors 1, 2 and 4, but 4 was already visited earlier. In fact 4 is where we came to 0 from in some sense. Right? So we now mark 1 and 2. So now you can see actually that everything has been marked, right? And 1 and 2 get into the queue. So at this point, in principle, everything has been marked and you could stop. But this is not how BFS stops. BFS stops by checking that every visited vertex has been explored, right? So what we will do now is we will go to 3 and explore it. But we find that all the neighbors of 3 are already visited. So exploration does not add anything to the queue. It only removes the 3 from the queue. Next, we explore 6. Similarly, all the neighbors of 6 have already been explored. So exploration of 6 only removes 6 from the queue, does not add anything to the queue, doesn't mark anything new. Similarly, we explore 9, again nothing new. Explore 1, again nothing new. Explore 2, again nothing new. And now the queue is empty. I have run out of work to do. So I have processed every vertex that I visited during my breadth first search. And as a result, I have marked all the vertices which I could visit starting from 7. Right? In this particular case, you can see obviously from this graph that everything can be reached by some path or the other from 7. So everything is marked as true. So this is breadth first search. So now we know, for instance, that we can reach 1 from 7 because everything was marked as true. So visitor of 1 is true. So clearly there was a way to go from 7 to 1. But this information that we have recorded in this visited vertex doesn't tell us anything about how to do this, right? So if we have visited of j equal to true after we have explored breadth first search from I, we know that j is reachable from I, but we don't have any information about the path. So this is now something that we can fix, right? So how did we get to j? We reached j because we explored j from some k. So if we keep track of how we reached each vertex, we can work backwards and extract the path. So visited j was set to true when we explored some vertex k. So we can say that the parent of j, okay, the reason that j got added to the visited set was k. So now if we go follow back from j to k through this parent link, k itself would have been added because of some other vertex. So we can look at parent of k. So maybe parent of k is some vertex L. So we go to L and we look at parent of L. Everything was eventually traced back to the starting vertex. So that is what marked the first set of vertices visited. So in this way, we will walk backwards and find the reverse path, which we can then of course enumerate in the forward direction and be done with it. So this can be done along with breadth first search with no extra cost except that we record more information. So as before, we start by setting visited to false. We are again starting with 7 so that we just have the same familiar computation to do. But now we have this extra column called parent, which records the parent, that is the vertex from which this vertex was marked as visited. So as before, we start by marking 7 and adding it to the queue. And then when we process 7, we add 4, 5 and 8 as marked, but we also set the parent of 4, 5 and 8 to be 7 to indicate that I came from here. Okay, so let me draw an arrow like this. So it says that I came from here. That's what this parent is saying, that I came this way. Right? So whichever way you want to think of the arrow as going, right? It's pointing to the vertex which marked it. Now when I process the 4, similarly, it's going to mark 0 and 3. And for 0 and 3, now the parent becomes 4 because that's how they got marked. 0 and 3 did not get marked by 7, they got marked by 4. Same way when I explore 5, the parent of 6 becomes 5. Same way when I explore 8, the parent of 9 becomes 8 because I got to 9 from 8. And finally, when I come to 0, then the parents of 1 and 2 become 0 because 0 marks them, right. Notice that 7 doesn't have a parent, and that's because we started the search at 7. So 7 got visited because we initiated the breadth first search at 7, not because some other vertex marked it, right. So except for the source vertex, all the other visited vertices will have a parent node marked in them. And now we can recover this information, right. So we come back to the end, and finally after we have explored everything, we have emptied the queue and breadth first search is over. Now we can ask, for instance, what is the path from 7 to 6, right. So the path from 7 to 6 that breadth first search discovered, well, I go to 6 and 6 says the parent of 6 is 5. So 6 says I came from here, right, and 5 now says I came from 7. So by following these parent links, I trace back this path from 7 to 6 to 7, and I read this path in reverse and I get 7, 5, 6. Right? So here is a longer path. What is the path from 7 to 2? So 2 says I came from 0, 0 says I came from 4, 4 says I came from 7. So therefore, reading it backwards, it is now 7, 4, 0 and then 2. Right. So in this way, by keeping this parent information as we are exploring the graph, we also record the path for every reachable vertex, or a path for every reachable vertex from the source vertex. So how about the distance, right? So we have explained that BFS explores neighbors level by level. So in some sense, the level of a vertex indicates the earliest that I can get to that vertex from the source vertex, right. So all the vertices which are level 1 could be reached directly in one edge from the source vertex. Anything which is at level 2 is reachable from level 1 but was not reachable directly, so I need 2 edges to reach it, and so on. So the level gives us some notion of distance from the source vertex, and can we do that? Right? So it turns out that we can modify our breadth first search. So instead of just keeping this true false information for visited, we can replace it by this level information, right. So every vertex which is reachable will have a level which is 0 for the source vertex, and it is 1 or more for every other vertex that is reachable. So since the minimum level is 0 for any reachable vertex, I can initialize the level to be -1. So any vertex whose level at the end remains -1 is as good as something whose visited value was false, that is, I never reached it. Otherwise, what I do is I set level to be 0 for the source vertex, assuming that I am starting from I, and whenever we visit a vertex j from vertex k, we already have a level assigned to k, so we assign the level of j to be the level of k plus 1. So it should be clear that because we are doing this level by level, the length of the shortest path in terms of number of edges that we have to travel is given by the level. So if I look at level of j, I know exactly how many edges I need to take to get from I to j. There might be longer ways, but there is no shorter way. So here is that breadth first search again. So I have now replaced this column visited by this column level, and as we said before, we put all the levels to be initially -1. So now we start with our favorite starting point 7. So we start by setting this level to be 0, right. So instead of setting it to be true as visited, we set its level to be 0. Now when we explore 7, its neighbors get level 1. So 4, 5 and 8 are all at level 1. Now when we explore the neighbor of 4, right, then explore the neighbor of 4, I get to 0 and 3. So these now have level 2 because the level of 4 was already 1. So it's 1 plus 1 is 2. Now if I explore 5, though I am exploring 5 after 4, the level of 5 was the same as level of 4. So what I can reach from 5 is also at level 2. Right? It's not that its level has increased because I am exploring it after 4. So both 4 and 5 were added at the same time. So they were both at level 1. I just happened to choose to process 4 before 5. So 6 also becomes level 2. Similarly, when I look at 8, 8 was also originally a level 1 vertex. So 9, which is reachable from 8, also becomes 2. So at this point, if we look, we can see that the two vertices which have not yet been visited are the ones which have level -1. Right? So that's of course going to be fixed next when I explore 0. So notice that explore 0 means that 0 has level 2. So these two become 3, because in order to reach 1 and 2, I have to first go to 0. and 0 was already 2 edges away, right. So this gives us the breadth first search, and as before, okay, so this is about paths, but as before we could also record we have the parent vertices, so you can get the path, but we can also get the shortest distance, right. So you can keep only the level, only the parent, both, whatever you want. So to summarize, breadth first search is a systematic strategy to explore a graph level by level. So remember that we said that broadly the way we explore a graph is to systematically propagate these marks from a source vertex to the neighbors, and so on. But we need a way to do this so that we don't go around and around in cycles. So we need a way to do it so that we terminate sensibly. So breadth first search is one such strategy. So what we do is we record the vertices which have been visited, and we maintain this queue of visited vertices which are yet to be explored. So exploration means explore the neighbors. Then we saw that we can add parent information to recover the path, and we can maintain level information to record the distance, which is the shortest path in terms of number of edges. Now what we will see is that in general, when we have a graph, we could record more information than just the edge. For instance, if you had a airline graph or a railway graph representing the route of a railway network or an airline network, then typically with each edge you would have associated with it some number which we will abstractly call a cost. Now the cost could be a real cost, it could be the price of a ticket to go from this station to that station or from this airport to that airport, but the cost could also be a distance, it could also be how many kilometers this route travels, or it could be time. For instance, if you have a train, the same distance could be covered in different times depending on the quality of the tracks and the number of stops in between. So in general, to go from one point to another point, you have to traverse real time or pay some real money or spend some distance traveling. Say supposing it's a road network, then it will give you a measure of how many liters of petrol you would expect to consume to complete this distance. So in these kind of graphs, which are called weighted graphs, the shortest paths are no longer just in terms of the number of edges. We could have a short edge, a single edge which has a very high cost, right. It could be that a direct flight costs much more than a flight which goes by an intermediate airport, because the airline is trying to encourage people to take these flights to unpopular airports in order to fill the planes, right. So it's not always that the shortest number of edges is also the shortest path. So we will explore this separately when we look at weighted graphs.